signal. All right, so before we go ahead and get started, you picked up the homework. Yeah. Oh, actually, I think those are out here. No, you don't want that one. Okay. Yeah. You have your bachelor. Yeah. Okay. Anybody else need a copy of the notes? Okay. All right. Okay, where's your bachelor? All right. Let's go ahead and fill that out for me. Okay, so you picked up the homework on the way in. Now, we're not completely done with the notes. We're going to finish that up on Monday. I'm just going to introduce you to secant and cosecant today, and then we'll do some transformations on Monday. But we've gotten through the majority of it, so you can definitely get started with it. The homework is posted to the website. So the way it's going to work next week, the homework is due on Wednesday, is when I have it due right now. And then on Friday of next week, that's when we have our quiz over this material. The reason it's on Friday and not Thursday is we have the pep rally. Okay, and last time my 8th period was completely wiped out, so I don't want to run that risk again. Okay, so let's take a look at what we got here. Now, I went ahead and put together this little summation. This is basically everything we've done so far up to this point, because when we're going to graph these trig functions, remember we look at it horizontally and vertically. Okay, for horizontally, we go ahead and create a compound inequality, and we have boundaries depending on what it is you're graphing. Sine and cosine, and what you're about to find out, coming up quick, cosecant and secant, their boundaries are going to be 0 and 2 pi. For tangent and cotangent, we used asymptote boundaries. Tangent between positive and negative pi over 2, and then cotangent between 0 and pi. And then vertically, we look at a combination, of ones, zeros, and negative ones. What did the no solution symbol refer to? Again, that's one of our asymptotes, because tangent and cotangent, they have periods of pi radians. And if you're wondering, again, where do those values come from? For example, tangent, one of its branches, it curves up to the right. So think about the 3 points that we were looking at. So negative 1, 0, 1, it's coming straight from those points. Just the same thing for cotangent. Okay. And then when you want to fill in the missing x's on your table, upper value minus lower value, and then divide by 4. Okay, so this is just a combination of what we've all been talking about for basically a couple of weeks now. All right. So let's take a look. The cosecant and secant functions are reciprocal functions. You remember how tangent and cotangent, we rewrote them in terms of sine and cosine? And then I used one to graph it. We're going to do the same thing here. And we're basically going to use the reciprocal as kind of like a skeleton or a foundation to help me get the graph that I want. Okay, so I'm going to first change this x here to theta. And I'll explain why I'm doing that in just a second. So cosecant of theta, can anybody tell me what the ratio is? It's what over what? R over, was it? Y. R over y. Okay, so r divided by y. Okay, so we're going to substitute in for these variables. Let's say we're on the unit circle, so the radius would be what? 1. And what trig function is y? Sine. So sine of theta. So because sine of theta is in the denominator, this is what we call a reciprocal function, one of the many identities we're going to be looking at next month. Well, wherever sine of theta equals 0, that's where cosecant is undefined is going to have an asymptote. So that's our first step. We're going to go ahead and graph sine. And remember, we're going to do this lightly because we're going to be removing it when we're done. So sine starts with a 0, then a maximum of 0, minimum 0, and we're going to continue this pattern over into the other area here. So this is what we're getting for sine. There we go. Now think about what we've done over this past week. What am I referring to when I say it equals 0? It's where sine touches what? The x-axis, yeah. So I'm looking here. Well, I can see the y-axis, 0. That's going to be an asymptote. We're going to have one at pi. We're going to have one at 2 pi, negative pi, negative 2 pi. And remember, this pattern is going to continue forever. In fact, you'll notice it's in multiples of pi. Your domain here to find the asymptotes The formula is pi k, where k is an integer. You just start plugging in integer values and you're good. Now, at this point, normally we'd go ahead and get rid of sine, but we're going to keep it for just a second. We're going to focus on sine's maximums and minimums. Wherever sine has a maximum, you're going to have a branch that opens up. Now, it looks like a parabola, but it's not a parabola. We're going to refer to those as branches. A parabola is constructed in a very specific way. These are going to look the way they do because they're bound by the asymptotes. So I'm going to have one opening up there, one opening up here, and everywhere I have a minimum, I'm going to have a branch opening down. So there's going to be one here, and then, oh, I don't know why I drew that one there. One here. Probably fit another one. And there we go. Once you have those in, now we can go ahead and remove sine. So let me just pull that out of the way. There is cosecant. Now, the thing about cosecant, it also has a period of 2 pi radians. Its period has to include both an upward and a downward opening branch. So that would be one period of this graph. Okay, it's 2 pi, just like sine and cosine. All right. And you'll notice the range, it is infinitely tall, but vertically, there's this gap. Vertically, nothing exists between -1 and 1. Okay. All right, and there you go. Does anybody have any questions on that? Pretty easy? Okay. We're going to do the same thing when it comes to secant. Okay. And this is right here is all we got today. We're almost done. So let's go ahead and get rid of this. All right, now this is why I went ahead and changed that x to theta, because secant is going to be r over x. And I didn't want to have those two x's there, kind of confuse people. So I just changed the variable. Well, let's say we're still on the unit circle. The radius is 1. But what is x? It's a trig function. That's cosine. All right, so this is one of our reciprocal identities. Oh, someone died. Hey. All right, so wherever cosine of theta equals 0, secant is undefined, we're going to have an asymptote. So it's the same thing. Let's go ahead and graph cosine, but do it lightly. So we're starting with a maximum, 0 minimum, 0 max, 0 minimum, 0 maximum. Okay, so let's see. Here we go. All right, so looking at this one, can anybody tell me one location where I got an asymptote? JJ? Okay, pi half, pi over 2. Got one around here. Okay. In fact, that's the first one you mentioned. I'm glad that you did. Look at your formula. The asymptotes are always going to be multiples of pi radians away from each other. So for that formula, they started to begin with pi over 2. We also have one at 3/2 pi, -1/2 pi, -3/2 pi, and again, it continues in both directions. Now, it's going to have branches similar to cosecant, but where do you think they are? Like, where are my branches going to be? How will I know where to locate them? What do I look at for cosine? The maximums and the minimums. Everywhere there's a maximum, you're going to have a branch that opens up. Okay. And everywhere there's a minimum, you're going to have a branch. Remember, a branch, not a parabola, that opens down. Okay, and there you go. That is secant. Let me go ahead and get cosine out of there. And just like cosecant, one period is going to have an up and a down branch. Just like that. Okay, so basically what I'm going to show you on Monday is we're going to go ahead and graph these by first graphing its reciprocal. Okay, and then we'll go ahead and do the same process, but I'll wait till then to show you. All right, are there any questions? That's all I got. Okay, so let's go ahead and shut that down. Bless you.